What on earth are phasors?
Well, essentially, they are vectors on a 2D complex plane. The length of the arrow determines its magnitude. They can be represented by complex numbers or vectorially. More importantly, what are phasors actually used for? They allow for simpler calculation of parameters in AC circuits. They provide an efficient means of analyzing an oscillating function. They are helpful for engineers and physicists. Moving on to more amazing applications. Let's represent the sinusoidal wave with the help of phasors. Now, how would we do that? First, let's make things easier for ourselves by marking the time period at which the wave peaks. The distance between the peak and the axis is known as the amplitude. On the other hand, we have a vector denoting the radius of a circle. Its vertical component will denote the magnitude of the wave at certain time intervals. When the angle of the vector changes with respect to time, the vector rotates, where its vertical component denotes the magnitude corresponding to the wave at certain angles. It's a beautiful way to truly understand the complexity and nature of the wave. Now let's move on to phasor algebra. In phasor addition, let the phases be Z1 and Z2. The sum of the above two phasors can be shown diagrammatically. Thus the resultant phasor, which is the sum of the other two phasors, is given as, while the angle of the resultant phasor is represented as. Coming to phasor multiplication, when two phasors Z1 and Z2 are multiplied, the product phasor will have the magnitude equal to the product of the magnitudes of the above two phasors, while the angles will be added. Moving on to phasor division, when two phasors Z1 and Z2 are divided, then the new phasor will have a magnitude equal to the division of the two phasor magnitudes, while the argument angles will be subtracted.
Well, that's all phasor algebra that there is. Easy, isn't it? I have made a summary table for your convenience. Thanks for watching. Please come back next time.